Okay, so welcome back to Unit 2, studying dynamics. So for the rest of the videos, we're really going to look at applications of Newton's laws. The first two videos here really focused on what are Newton's laws. From here on out, we're going to talk about these applications of the laws. And the first thing we're going to look at is weight and normal force. Okay, so one thing to note, weight and mass are not equal, right? So they're two different things. Mass is that physical quantity associated with inertia. Weight is going to be something completely different. So what is weight exactly? It's a force that is caused, or the force that causes an object to accelerate to a planet is called the force of gravity or gravitational force. Now, the magnitude of that force is what we call weight. And so the equation for the gravitational force is the vector gravitational force equal to mass times this g with a vector, right? And so this is what we call the gravitational field strength. And it's actually reported in newtons per kilogram as opposed to meters per second, meters per second squared. But if I take the magnitude of this gravitational force, that's where I end up with the weight, okay? So the magnitude of the gravitational force is the weight of an object. Now, what happens is when an object is at rest on Earth, this force does not disappear, but there's something else that balances it, okay? So one thing to note is that the gravitational force always acts down, okay? Now, if we think about a book on a table, there's going to be two forces acting on it, right? And so you get the force of gravity, which we just talked about. So that's a downward force, right? Because gravity is always acting down. Okay? Remember, it has a magnitude of m times g. But there's going to be an upward contact force balancing this out that we call the normal force. All right? And so one thing to note is that normal mathematically means perpendicular. Okay, so it's always going to be perpendicular to the surface that we talk about or that we're looking at. And then finally, when doing problems from here on out, you're going to look at this vector sum. So when doing problems involving this particular situation with weight and normal, you're going to set the vector sum equal to 0 because these forces are going to balance each other out. If these two forces don't balance out, the book will fall through the table or it will fly off the table, depending on which one is greater. And so when we talk about a vector sum, basically we're just summing the forces. That's going to be like F1 plus F2 plus dot, dot, dot. Now, this is pretty easy because the forces are going to act in the same direction in terms of they're both vertical. But sometimes you may end up with forces that look like this. So like if this is F1 and this is F2, well, the vector sum is what we call the net force, okay? And we'll define that here in a couple of videos as well, right? In this case, it would be the Pythagorean theorem, right? Because you can see we just created a right triangle. Okay, so let's look at a couple examples where this is applied. So you got to here. So basically, you got a friend who's giving you a gift. We need to find the gift is 10 kilograms. We need to find the weight of the box and the normal force exerted on it by the table. Now our friend's going to push down, right? And then we're going to find what does the normal force exert. And then in the last situation, our friend's going to pull upward, okay? And then we're going to figure out what the normal force would be in that situation, okay? So again, I mean, there's two basic forces. You got the weight down, so for the first situation, and you have the normal force up. So if I do the vector sum, I'm going to do Fn minus Fg. I'm going to set that equal to 0 because there's no acceleration. The book is just sitting here. And so what this tells me is that my normal force, so my Fn, will equal my weight. So those two values are going to be equal. So it's just going to be m times g And so that's going to be 10 times 9.81 or 9.8 or 10. So our answer to part A is that they both have a value of 98.1 newtons. Okay, part B, my picture changes just a little bit. Now I've got this downward force from my friend, we'll call it force applied. All right, so how does that change my vector sum? Well, my vector sum now becomes the sum of the forces equals Fn up minus Fg down minus Fa down. Right, and so I'm looking for that's going to be equal to 0. So we're going to set this equal to 0, and that means my normal force will be Fn equals Fg plus Fa. So note that the normal force is going to get larger because you're adding more force down. And so we're saying 98.1 newtons plus 40 newtons, and it's going to be an answer of 138.1 newtons. Okay, so as expected, our normal force would go down, or excuse me, go up. All right, so now in the third case, I'm going to erase my normal force now, or my applied force, because now our friend is lifting up. All right, so our applied force is up, and so we do the same thing. We sum the forces. So we have Fn plus Fa now minus Fg, and something you'll see is that our normal force will now be less than what it was before. So we set that equal to 0, and so I'm going to say Fn equals Fg minus Fa, just some simple algebra there. So it's going to be 98.1 minus 40.0, and we find that our normal force is now 58.1 newtons. Okay, so you can see if I push down, the table needs to add more support. If I try to pull up, the table is going to provide less support. Okay, so now the next question that pops up here are these what are called apparent weight questions. Okay, so this tells us that we have a woman descending an elevator that briefly accelerates downward. Right, she stands on a scale that reads in kilograms. During this acceleration, what is her weight, and what does the scale read? B, what does the scale read when the elevator descends at a constant speed of 2 meters per second? Right, and so basically, what's causing this apparent weight, which we call Fg prime, okay, is the normal force caused by the floor. So again, we're going to do our vector sum. So the sum of the forces is going to be equal to Fg prime up, which is, again, this is the normal force from the floor scale, okay, but we just call it apparent weight. And in this case, right, she's accelerating at 0.2 g downward, right, and so it's going to be, okay, so it's going to be this acceleration times her mass. So we're going to say, so we're looking for Fg prime. So again, I mean, her weight is just going to be simply 65 times 9.8, right? So mg is 65 times 9.8. It's kind of the first part of our question, and that's going to be 637. Sorry, I'm having issues with my pen right now. So that's going to be a value of 637 newtons. Okay, which then we come back over to our equation. So we're going to have Fg plus this whole 0.20 times g times our mass. So it's going to be 637 plus 0.2 times g. We'll just call that, apologize. So it's 1.96 times 65. And so it's going to be 637 plus this is going to be a downward acceleration. So this is actually going to be a minus. Okay, so 65 times 1.96, sorry, It's going to be 127.4. It's going to be a minus. So 637 minus our answer. So it's going to be approximately, the scale is going to read 510 newtons. Okay. Now, what would her mass, essentially what does, so the second part of the question says, what does the scale read? Which means what is her, what essentially is her mass? So we would just take this number, so we take our Fg prime and divide it by our 9.81. So M would be Fg prime over G. So it's going to be 510 over 9.8, which is going to give us a 52 kilograms would be her mass. Okay. Now part B, what happens is it's the same situation, but the problem is constant speed means no acceleration. So that just tells you that her apparent weight would equal her weight, which would be 637 newtons. Okay, there is a little bit of a shortcut formula here. So apparent weight would be the mass times G plus A. But this A, again, you would have to realize if it's positive, it's negative. So if it's more than or less than her actual weight. Okay, so again, after this video, we're going to keep working on